Please, go ahead.
Okay, well, yeah,
So,
Is
so
it-
Alex is giving you compliment for your head for him. On the chat, the chat is right.
okay.
Chat message. Okay.
Okay, thank you. So you may or may not have remembered me from Monday. But I spent a lot of Monday morning trying.
Cheerleader last night.
Yeah, or as a cheerleader, you do remember that, I'm sure. So Monday morning, I was sort of giving you basic background on what you might call classical potential theory. So maybe a little, it wasn't so exciting and all of that. And is there really anything interesting in this classical potential theory setting? And today I hope to convince you that there is. That for me, what's really exciting sometimes is that you look at a problem, it looks quite innocent, you start investigating it, and you find something unusual, something unexpected. You might call it a phenomenon. It's good for grant writing. You say a phenomenon, we're going to study phenomena, and it's transitional and so on. So you might want to use those words in your grant proposal. So transformative. Okay, that's another word. So you can copy these down. These may be more valuable than anything I have to say today. Sprinkle them in your grant proposal. So today's, well, I sort of changed the subject. I was going to talk about polarization, which is a subject I've been trying to push quite a bit, and I've had the opportunity to work with Mirsha on that. But I decided that that it would be a good complement to my talk on Monday and sort of tie things together with some of the other talks that we've heard to discuss some recent energy problems. And it sort of started with Jalil Chaffee, who is at École Normale Supérieure in Paris, and he was at a meeting that we had in Providence at ICERM, and he was interested in log gases and fluctuations and so on. And then he asked me about this minimization problem. I said, well, I want to minimize the log potential, but I want to do it in 3D. I want to do it in 3D, not the usual 2D. I want to do it in 3D, and and there's an external field, say a quadratic or confining external field, and I want to know what is the equilibrium. That seemed like a very innocent problem, but it led us down the path that I want to describe a little bit here. It's as shown here. It's joint work with Jalil and also Rob Wormersley from UNSW. You've heard his name before as an outstanding person in terms of algorithms for computing minimum energy points. So regard this talk as not so much an announcement of results, but as an invitation. So there are more open problems here. And although it's a very classical subject, I hope it will inspire you to think a bit about some problems. Okay, so the motivation, part of it has to do with integral identities. So we started working on this problem of this log gas, and we came across some interesting integrals. So this looks pretty innocent, I would think here, right? It's just a log term, and there's a parameter lambda runs between 0 and 1. But other than that, we're integrating a log times this polynomial of degree 1 time with respect to a very common distribution, r over the square root of 1 minus r squared. And so we go to Mathematica, we go to Maple, we say, what's the answer to this integral, right? Tell me what this is. And it doesn't say anything. It says nothing. Okay. So I was a little somewhat disappointed. A similar situation happened here that we came across in our problem, which deals with elliptic integrals of the first kind. That's this function k here. And well, it's evaluated at 4 lambda r over r plus lambda squared. This is actually quite common. It's called this is Landon Transformation, and r and lambda both take values between 0 and 1, and that's the same is true of this 4 lambda r over r plus lambda quantity squared. So this also is a fairly innocent looking integral, and we ask our software, no answer. We run to the tables of integrals, classical tables of integrals. Prudnikov is one of them. No. We write to our friends. Have you seen this integral? Have you seen this? All our special. No, we haven't seen this integral. Okay. And then thirdly, here's one. Okay, it looks a bit more complicated. It involves the hypergeometric function 2f1. So that's defined at the bottom of your page here. If you haven't seen it before, it is a rather commonly occurring special function. And there, again, we wanted an integral with this parameter lambda. I don't know if you can see my light here, can you? Okay, so there's just one parameter lambda that runs between 0 and 1. So we want to know what this is. Okay, so we got no help from either existing books or from existing software. But it turns out that all three of these integrals have very simple expressions in terms of a quadratic polynomial in lambda. And the way we arrived at these formulas was through studying a potential theory problem. And so I want to talk about that particular problem. And by the way, if you run to your Mathematica, and okay, check me out. So if you do this first guy here, this is what you come up with. At least that's what I did. I came up with. So that's for the first part of that. And that involves 3 F2s and so on and so forth. Okay. So rather strange. Okay. All right. So let's move on to where we got these formulas from. How do they arise? So a little bit of history here. I want to talk about Riesz energy problems. Of course, that's been a theme throughout this meeting. And you should know which Riesz we're talking about, right? Because they're the famous Riesz brothers. And we're talking about the younger Marcel Riesz. So there he is looking quite happy. He seems that he just solved the problem, an equilibrium problem. And I want to describe it to you, what problem he solved. So the problem is very simple to state. Just find the equilibrium measure on a ball in RD. So you have a fixed ball, fixed radius, fixed ball in RD. And what we're going to be talking about is the equilibrium measure for the Riesz S kernel. So we've seen this many times. So denoted here by K sub S. And here for the argument, I'm going to take X minus Y typically. We do allow S to be negative, not too negative, because we don't want to lose uniqueness, total positivity, that sort of thing. We want to maintain uniqueness, so positive definiteness is important. We lose that if we get down to -2 or below. But for S, say positive or even 0. So when S is 0, we take the Riesz kernel to be just simply log of 1 over distance, or minus the log. Okay, so that's the kernel that we're dealing with. And then we look at its energy. So for a particular probability measure, mu. So take a probability measure, mu. This will be supported on the ball.
So that's not on the surface of the sphere, but that's the
ball. It's a ball. It's a d-dimensional object. We're in RD, and it's a d-dimensional ball centered at the origin. Okay. All right. Good to point out, because that will show up later. So this is so the energy. So remember from Monday's talk, right? We talked about the continuous energy problem. And what is that? That's simply integrating your kernel, here as a function of x minus y with respect to the mu cross mu. Mu is a probability measure supported on the ball. You can also think of this energy as the integral of the potential, the S potential against your measure mu, the same mu here. So what is the potential? The potential is just the convolution of Ks with the measure mu. So that's our energy, continuous energy. And remember, when we minimize that, which is what we want to do, minimize it over all probability measures on our set, our ball, then we get what's called the Wiener Constant. I'll come back to this in a minute. But okay, so B sub r is our ball to fix the situation, ball of radius r in RD. And we want to find the equilibrium measure. In other words, a probability measure supported on the ball that attains the minimum continuous energy here. Seems like a simple problem, right? Well, Reese worked on this some years ago, and 1930s, in fact. And he came up with a solution, which is the following. It depends on S. So when S, the Reese parameter is less than or equal to d minus 2. So why is d minus 2 so important? We've seen this before. So when you're in RD and you take your Reese parameter be d minus 2, you got your Coulomb potential, your Newton potential, right? It's harmonic. All right, it's a fundamental solution to Laplace's equation. Life is good. When S is less than or equal to d minus 2, your kernel, your kernel case of S becomes super harmonic. And when it is less than d but greater than or equal to d minus 2, the kernel is subharmonic. So we're talking about this S kernel here, okay? I take its Laplacian, and it's going to be greater than or equal to 0, or the Laplacian is going to be greater than or equal to 0 if S is between d and d minus 2, okay? All right. This is the typical cases that have been studied. S equals d minus 2 and S between d minus 2 and d. And he found this formula for the equilibrium measure. Namely, when S is less than or equal to d minus 2, the equilibrium measure is supported on the sphere, the surface of this ball of radius r. So sigma sub r is just the uniform probability measure on the surface of this ball, sigma sub r. On the other hand, once we get to the Coulomb case or beyond the subharmonic case, then it's no longer, the mass is no longer supported exclusively on the sphere. It rather is supported everywhere on the ball, depending on where you are. There's a different density. The density is given here. Okay, this is the density that depends on your dimension d and the Reese S parameter or strength parameter S. And okay, so here is a fairly nice, reasonable, simple formula.
So excuse me,
Yeah.
that means that the measure is 0 inside the sphere in this first example. If it's
Yeah, there's no mass in there.
There's no mass.
No mass. Correct. Okay, so that's sort of a phenomenon too, right? Sort of a phenomenon. Okay, sort of a phenomenon. All right. Cool. All right. So what about the proof? Should be simple, huh? Simple. Just find the probability measure that minimizes the energy on a ball in RD. What could be more fundamental, right? Well, the way Reese did it, and the way you'll find it in standard books, is that they establish this integral identity. So here's our Reese kernel written with the power to the minus S instead of 1 over absolute x minus y to the S power. Here is the distribution we just saw above, where I put y instead of x. And what he showed was that this integral is constant. It's constant on the ball, remember? And this is a potential. This is the S potential of this distribution here with respect to Lebesgue measure. And if you've got a potential that's everywhere constant on your set, you're at equilibrium. there's not going to be any charge that's moving, right? So you're at equilibrium. And so that's the way to establish that you have found the equilibrium measure. But I want to look up the proof of this, okay? And so where do I go? Well, I could go back to some of Reese's papers. Actually, he just did it, I think, for R2. And I think in the later paper for R3, I want to do it in RD. So we try to look for proofs. And I guess the one that's most often quoted is from the book on modern potential theory by Landkoff. So remember at the beginning of the course, I mentioned that was one of my favorite references, Landkoff. And there's an appendix that has, I don't know, 2-3 pages of calculations on this integral. I mean, this is, how do you deal with this integral, which has a singularity, obviously, okay? It's a singular integral. How do we evaluate that? And so they go through a number of transformations. There's quite a bit of tricks, geometric tricks, and so on. And it's not very gratifying, as someone at the meeting said. I guess it was Giro. You sort of walk out of the restaurant, and you're still hungry, right? There's a lot to digest, and then but you don't have much of a feeling why this should be the answer, or what led you to this conclusion, and so on. So we try to help the situation, and that's in this recent paper in JMAA, Journal of Math Analysis and Applications, in which we give a detailed proof of the Riesz theorem and explain things that were left unsaid in Landkoff, and we even give some alternative approaches for coming up with a solution. But still, it's not completely gratifying. It's still taking 3 pages, okay? And how do you come up with the answer to that simple problem? So here's the challenge. Find a simple proof. In any case, okay, this has fascinated me, and but we are going to move on. So what's new here in terms of what we did? Well, in this case, I want to look at an external field problem. David talked about external fields, right? You talked about in equilibrium problems with regard to an external field. And so I'm going to deal now with a new energy. So that depends on the external field. This is V, is the external field. And it's going to be a confining external field. So it's going to force charges to remain in some compact set. And I'm going to take a very simple external field, as I'll indicate in a minute. So the difference between what we've seen before and what we're seeing now is the addition of this V of X plus V of Y. So we have charges that are repelling each other according to this Riesz potential, and we also have an external field acting. Okay? But I'm not restricting things to a ball. I'm working in RD. Okay, we're dealing with RD. We have an external field. That's all I'm telling you, right? Okay, and what we're interested in is the equilibrium measure. That is, we want to minimize this energy that involves the Riesz parameter and the external field. And we'll call that solution mu sub EQ, the equilibrium measure for this external field problem. Now, as long as we have some kind of confining potential, our Frostment conditions, which I introduced on Monday, those apply just as well. So remember, those were rather general conditions, and they apply. And what do they say in the case of an external field? They say that the equilibrium measure, the potential for the equilibrium measure, so there should be really an EQ here, the potential for the equilibrium measure plus the external field is going to be constant, essentially. That's because quasi everywhere, constant on the support of the equilibrium measure, and bigger than or equal to that constant everywhere else. And about this quasi everywhere, this small set of exceptional points, Alex Elassi is going to talk after when I finish, and he'll be discussing how we can often remove that situation if we have a nice set in a reasonable external field, and that's what we'll be talking about. So we can just not worry about this quasi everywhere business and just have these two conditions that characterize the equilibrium measure. It's the potential plus the external field being constant on the support and being greater than or equal to that constant everywhere in RD. All right. So, all right. So what's the simplest situation we can deal with? And that's the Coulomb case. Okay. So the Coulomb case, as I mentioned, is a case where we know that the Laplacian of the Riesz kernel is just minus a constant times delta naught, so it's a fundamental solution. The constant is given here in these formulas as being the surface area of the sphere. This is the sphere of dimension d-1 embedded in RD. And for d naught 2, that's for d equals to 2. For d naught 2, it's given by this formula here. Okay. And so one of the results that we get out of the Frostment conditions that you just saw is this, namely that if your equilibrium measure has a support whose interior is non-empty. So suppose that's the case. I'm assuming that's the case. Suppose you're restricting yourself to the interior of the support. If indeed the measure has a support with the interior, then the equilibrium measure is, in the sense of distributions, the same as the Laplacian of V divided by that constant that appeared just above. How do I know that? How does this come about? Well, just look at the Frostman condition here. Look at this condition of equality right here. And take the Laplacian, okay? Remember that we're dealing with the case where S is d-2. That's the only case I'm talking about right now. S is d-2. If I take the Laplacian of this first portion, then I recover the equilibrium measure, right? And then with a minus sign, it's a minus C sub D. So remember that minus C sub D business that we had, I think. Well, okay, I guess it comes later. Here, the minus C sub D. So we take the Laplacian and we get the minus C sub D times the equilibrium measure plus the Laplacian of V equals what? Equals 0 on the support, okay? Laplacian of a constant. So that gives me my formula right here in the sense of distributions, okay? Great. All right. So from here on out, we're going to take a very simple external field, just the modulus of x to the power alpha. Okay, what could be simple? All right. So that's all we're taking, this guy here and the recessed kernel, and we're after finding the equilibrium measure. Okay. So what is indeed the equilibrium measure? Let's see. Here we have a formula for the equilibrium measure. Should the equilibrium measure have a support which with interior? Okay, we have a formula for it here. Because when I take the Laplacian of the modulus of x to the alpha, it gives me the modulus of x to the alpha minus 2 times a constant. Okay. So that's okay. So that's a reasonable expression, but it doesn't give me exactly the answer, because how do I know that? How do I know that the support is a ball? This is the whole equilibrium measure, not just a piece of it. Okay. This is the claim here that this is the full guy. So how can I conclude that I actually have the full ball? Well, you can just go ahead and try to find the radius, because that's not what's explained here. The radius is not given. Okay, we only know what the distribution is with respect to the vague measure, the absolutely continuous part of on the interior. So we need to find the radius. So that's okay. We have a problem which is radial. So what can be the answer? Okay. So V is modulus of x to the alpha. What could be the answer? It's radial. So your support's going to be radial, right? You have uniqueness. We have a situation where we have conditionally positive definite, strictly conditionally positive definite. That's easy to show. So there will be uniqueness of our solution. Everything is sort of radial. So the solution has to inherit that being radial property. Okay. So how do we go about determining the radius? Oh, by the way, if it's radial, does that mean it's a ball? This is an important question. I know that the answer is going to be radial. So, hey, the answer should be a ball, right? No, it's not. It's a confining potential.
Could just be a sphere.
It could just be a sphere. Is that all? That's it. Just a sphere or a ball, right? It
Yeah.
could be several spheres. Could be so a region between two spheres, right? What do you call it? An annular region? It could, okay. It could be a lot of things, even though you know it's radial. You're in your gut, you know the answer should be a ball, right? But just by using the radial property, that doesn't tell you it's a ball. There's still a lot of other options that can occur, right? So, okay, so what can we do to try to find the radius if we believe that the answer is a ball or even some other kind of region that's radial? How can we go about finding its support? Okay, so remember, we're working in the whole space. I have a confining potential. It's going to confine it to a compact set. What is that compact set? I know the density, at least on the interior, when I have Coulomb, okay? When I have Coulomb. So what can we do? What can we do to find this radius in this case and in other more general cases? So I may attempt something which I might regret, which is to switch over to my iPad and write a little bit on my iPad. Okay, so this is going to fail for sure, but I have a backup, which is this guy right here. Okay, but I have insurance. So stand by and let's try this. I'm feeling encouraged this morning. So I got to stop share. Okay, now I've got to get back to screen share. Then I've got to share with my iPad. Sorry, this takes several steps. I also have to install a software. I love technology. Then I've got to let's see, I've got to try to connect here. This is a hard part. And see if I can do screen monitoring. Screen mirroring here. I hope this is worthwhile after we get, it's not, I don't think it's talking to my iPad. So the problem is, how do we find the support? How do we find the support? Even if we know it's a ball or we know it's a sphere or something like that, how do we find it? Okay. So so I'm going to write up here. Hopefully this will be readable. There are two sides to this.
That's for recharging.
Recharging.
Yeah.
So this should work.
Yeah.
Okay. So let's see if this works. Okay. Frostment conditions. Okay, so what is a Frostment condition? Remember, here's what we have. We have this potential, u sub s, for our equilibrium measure, which I'm denoting by mu sub EQ, plus the external field, and that's equal to some constant, which I'll call here F sub E, on the support of the equilibrium measure. And it's greater than or equal to that constant everywhere else, but otherwise. Because remember, our problem is formulated in RD. So that's the Frostman condition. Okay, now, so the idea is to define what call a functional F, an F functional. So we're going to define for a compact set A. So there's any compact set in RD, but I want to have positive capacity. The capacity of A is positive. And I'm going to define this, no other choice, but I'll just call it an F functional, F sub S of A. So it's a function on these compact sets. And it's defined to be the Wiener constant, the S Wiener constant for the set A, plus the integral of your external field against the equilibrium measure on the set A without external field. So what is this? Mu sub A is equal to the equilibrium measure on the set A without any external field. Okay, and so this Wiener constant is like we used it on the first day. That's just going to be for us the double integral of our kernel. And here I'm going to take an S kernel. Well, I'll restrict S in a moment, but of against d mu xa d mu y. Okay, so that's the Wiener constant. It's the minimum possible energy for probability measures supported on your fixed compact set A. And so for every reasonable compact set, I define this functional here. And I don't know whether you can see down below here. So the theorem is this, that if you're in the subharmonic case, if you're talking about S bigger than or equal to D minus 2 and less than D, then the support of the equilibrium measure for your external field problem. This is the guy with the external field. That's the guy we're after, right? Use of EQ. Then this guy gives or minimizes, I should say, minimizes F sub S of A. Okay. So here's the idea. Suppose I have a feeling that my answer is a ball. Well, we know thanks to Reese, what is the equilibrium measure on a ball, right? So we know mu sub A, we know also this Wiener constant for the ball. And I can look at balls of various radii. And then what this theorem says is, hey, look at the minimum value of this function. And that minimum value is going to be attained on the ball that gives you the smallest value for your F function. Okay. Seem reasonable? So It's converting this problem into a one-dimensional one, if I know or have a good guess as to what the support is. So I'm thinking the support is a ball. So, all right. Do you want to see the proof? Yeah, is everybody up for the proof?
Yeah.
Okay. Okay. All right. It's interesting enough to have a proof.
Paul told us to always look at the proof.
Okay, and this is a ball here too, so great. There is a ball involved in this way too. All right. Okay. So one of the things that we need here for this theorem is this condition on S. We need a maximum principle. So because of our assumption on S, we know that mu sub S, and here this is any probability measure that mu sub S satisfies a maximum principle. Okay. All right, so what do I mean by that? I mean that if you have a bound for your potential on the support of your measure, that bound is going to hold everywhere in RD. Okay, so i.e. if mu sub this potential is less than or equal to a constant, say m, on the support of your measure mu. So this is any probability measure, really, compact support. Then u sub s, u is less than or equal to m for all x in RD. Okay, so bound on the support is in fact a bound on the whole space. Okay, why is this? Well, it's because in this range of S, we're dealing with subharmonic functions. Okay, so we're dealing with subharmonic functions, they satisfy a maximum principle. And so we apply that maximum principle outside the support. Okay, it's subharmonic, it's going to attain its maximum on the boundary, which is on your support set. Okay, and so that's pretty much the argument, right? It's just being subharmonic. So that's what we need. Okay. So so in particular, what do we know? We know that u sub s, u sub a. So here's, remember, this is our A is a compact set and it has positive capacity. So it has a finite Wiener constant. That this is less than or equal to the Wiener constant for your set A everywhere for all x in RD, right? Why is that? Because on the support, on the equilibrium support, this is an equilibrium without external field. On the support, we have equality, right? So the inequality certainly holds on the support. So therefore, it holds everywhere in RD. Okay. All right. So that's okay. So now what do? We look at Frostment again. We look at Frostment again, and in particular, we want to look at the fact that the integral of the potential. So now we're back to our original external field problem. We're dealing with the probability measure mu sub EQ. Okay. So this guy plus the potential plus the external field V, this guy is equal to or greater than some constant everywhere on RD. I'll call that constant F sub E on RD, and it, with equality on the support of. So Frostman tells us that this holds true. Okay, for this is the guy we're after, and that this inequality holds true. So what I'll do is just integrate I'll integrate this inequality with respect to mu sub a. So what do I get? I get the integral of u sub s, u sub eq, integrated with respect to mu sub a, plus the integral of v, integrated with respect to mu sub a. That's bigger than or equal to f sub e, right? Because this holds in everywhere, so it certainly holds on the support. Mu sub a is a probability measure, and so that's the condition that I have. But one of the things I can do is just use the reciprocity property. I can, whatever, Tonelli's theorem, essentially, right? I can interchange these two measures, the mu sub eq and the mu sub a. So this tells me that the integral u sub s mu with respect to mu sub a integrated with respect to mu eq plus the integral of v mu a is greater than or equal to this constant f sub e. Okay, but what did we observe earlier? We observed that this mu sub s of mu a, that's always less than or equal to the Wiener constant, right? So what do I have here? I have the integral. This guy's bounded above by the Wiener constant. I'm integrating it against the probability measure. So this quantity here is certainly no larger than the Wiener constant W sub S of A, right? So W sub S of A plus the integral of V d mu A, this is a V, is bigger than or equal to F sub E. Okay, but this is our functional, right? This is our F function right here. Okay. So it's always bigger than or equal to this constant. But what happens to this constant? What do we get here when A is the support of your equilibrium measure for the external field problem? We get equality, right? So with equality, when A is equal to the support of mu eq. And that's it. That's the proof. Simple, right? It's pretty simple, but powerful tool. Okay. That the support has to minimize this F function. Okay. Any questions about this argument? No? No. Okay. All right, great. Okay, so let's get back to the slides. And where are we? So here, in this case, what we could do is, just as I said before, we think the answer is a ball. So we try a ball of radius r. We know what mu sub mu with a ball is. We know what the Wiener constant is. We get a function of the radius of the ball. We minimize that, okay? And that value for r will give us the support radius. Okay. All right, so that's easily done. All right, now why isn't this moving here? Okay. So, okay, so where can we go from the Coulomb case, which is a well-studied case, to something more general? And one thing that's sort of obvious is to say, okay, well, we applied Laplacian one time in the Coulomb case, and we got a lot of interesting information, right? We knew what the density was, or if you're in the interior of the support of the equilibrium measure. Why not apply the Laplacian more than once? Well, that works great, provided that ultimately you end up with a fundamental solution to Laplace's equation. So where it's going to help you in the simplest situations are when S, the Riesz parameter, is D, the dimension of your space, minus 2n, minus an even integer, right? So we took n equals 1 and did the Coulomb. What happens if I take n equals 2? So in other words, your Riesz parameter S is D minus 4. What can I say about that? So if you apply similar argument, not a difficult argument, similar argument, what you get is that on the interior of the equilibrium measure, you can write down a formula in the sense of distributions for the equilibrium measure. Namely, you apply the Laplacian n times. There are these constants. Remember, you saw C sub d before, and here's a capital C sub dn, which is just expressed this way. In fact, it's given as a product. This is not working anymore. A product of the little c's, so on. Okay. So how we get these formulas? We get from the fact that if you take the Laplacian of the kernel with a Riesz parameter u, then essentially you get the Riesz kernel with a parameter u plus 2 with a minus a constant out in front. So, okay, so let's look at the next simplest situation. Suppose my S is d minus 4. What happens there? When V, this external field, is simply mod x to the alpha. Okay, so remember that the Laplacian of the external field, that's easy to compute. The external field is just mod x to the alpha. And if I take its Laplacian, here's my V, all I get is that external field, but now to a power alpha minus 2. All right, so there's a couple of things going on here. Here I have the Laplacian to the nth applied to V, but here I have a bunch of constants below. And if this constant turns out to be negative, if that constant turns out to be negative, then obviously this doesn't make any sense. And the measure, the equilibrium measure, has to be singular. So this gives us some information about when you don't have interior in your support. Okay, so it's a very simple result, but it is valuable because it tells us, for example, that if we end up with an expression that's negative, it can't be the equilibrium measure. So we have to have empty interior. All right. So okay. So one of the things that we did is to experiment, and this is thanks to Rob Marmersley. He has some really good software for computing these minimum energy points. And so we looked at the discretized problem, much as in David's talk the other day. So we look at discretized problem. Here's our discrete energy, and we want to approximate the equilibrium measure. I don't know. I'm experimenting. I want to find out what might be the answer to this equilibrium problem. And the idea is if I minimize this discrete energy problem, I should get an answer which is approximately the equilibrium measure. Okay, so that's the idea. And so what happens when we do this experiment? So, okay, so we need to talk about this graph. So for this graph, let's see if this is working. Yeah, so remember our external field is mod x to the alpha. And I want to start by looking at large alpha. So, well, large is 5 here, okay? If alpha is 5. So in this regime, what the simple result, the previous result said was that your measure is singular. And indeed, you can see here in this histogram, this is a histogram which is plotting the absolute value, the norm of your discrete points, okay, which are approximating your equilibrium measure. They're all congregating on a sphere of radius r, where r is 0.631. So this is indicating, the numerics indicate that you should get a sphere for your equilibrium support in this case. And you know it's singular from the previous result. Here we take alpha a bit smaller, and we get out when alpha is small, smaller to be 4, and we get the same situation when alpha is 3. The same situation when alpha is 2, so the important situation of mod x squared, then again, we get a support which is just the sphere. Okay, so what happens when alpha is less than 2? So that's the interesting part. And here's a situation here when alpha is less than 2, it's 1.8 in fact. And what we see is that there's quite a lot of mass on the sphere, sphere of approximate radius 0.5, but there's also other mass. There's other masses that are coming up here. So what is going on? Here's alpha, which is a bit smaller, same kind of situation. A lot of mass on a sphere and also mass with radii less than that sphere radius, and so on down the line here. So what exactly is going on in this situation? Okay. So that's the sort of main result. And so here's the case when S is D minus 4. And here is the sort of main result in this case. And that's that your equilibrium measure. So remember, our situation is we're working in the whole space. We have an external field, and here slightly generalized because I took mod x to the alpha and multiplied it by a scalar gamma here. So I've incorporated that in the answer. And what it says is that if your the alpha power here of your external field is bigger than or equal to 2, then your support is singular. Your support is on a sphere. Okay, this is the uniform measure on the sphere of radius r. And when alpha is between 0 and 2, and this is the sort of unexpected part, this you might call the phenomenon, what you get for the equilibrium measure is not something you would expect. You get a mixture. Your equilibrium measure is in fact a mixture of an absolutely continuous part, okay, absolutely continuous. M sub D is Lebesgue measure. So what multiplies it, the density involves beta, constant beta, and here another parameter F, but its equilibrium measure is given here, and the radius is given in terms of S and alpha and our constant gamma. S prime, by the way, is something for convenience. It's the same as S as long as S is not 0. When S is 0, it's equal to 1. So we found that the support, what is the support? The support is the ball, supported on a ball, but it is and has an absolutely continuous part and a singular part. It's not something that you would expect just looking at this simple problem in RD. If I have an external field of mod x to the 1/2, why should that equilibrium measure be supported on a ball together with a mass on the surface of the ball? And here you can see how this beta parameter, that's kind of indicating how much mass is on the interior of the ball versus how much mass is on the surface of the ball. Okay. And how that varies depending on alpha. So as alpha approaches 2, it just all concentrates on the sphere. Alpha is less than 2, you have an absolutely continuous part. So that's sort of the main result. Okay, I'm not sure how much time I have left. We're about close to.
Yeah, so it would be over, but I don't know.
Okay. All right. So I just want to show you some more, a couple of challenging problems, and we'll be done.
I mean,
Yeah, Alex will take over.
okay. So
Okay.
then it will- yeah, so then
Okay. Okay. All right. There's some special cases in 3 dimensions. If we take a non-singular kernel, say when S is -1, so we're just looking at minus the distance between X and Y, that's our kernel. And there we have to be careful because we may not have an equilibrium measure. It depends on whether if your confining field is not strong enough. But I don't want to spend time on that. Here is the answer to the original problem about log gases in 3D and what the equilibrium measure is there. Here, again, this is a situation where we have a super harmonic kernel and essentially a harmonic or external field. And okay, so the answer turns out to be a ball. And but I don't have time to go through the argument. So here's the challenge that we had to face to deal with both the super harmonic kernel and an external field which was subharmonic. We want to apply more generally the Laplacian, but it's non, the fractional Laplacian, which is what we want to apply for general alpha, is non-local, and so that's a problem we have to overcome. But what we used in the special cases I showed are the Frostman conditions. We applied Laplacian on the support. We used the radial property of the support, and also the dimension reduction of the Funk-Hecke formula, which we heard mentioned a couple of times in the talk so far. Okay, so what I just want to show you to conclude is some problems that we have not been able to solve yet. So this is the same simple situation of a recess kernel and an external field which is mod x to the alpha. So okay, very easy to get a grasp on, right? All right, so what happens when alpha is d less than 2 and s is d minus 3? Okay, remember we've solved the case s equals d minus 4. That was our main theorem there. So what about when s is d minus 3? So for example, you have you're in 3D and your s is 0. In other words, you have log gas in 3 dimensions, okay? And your external field is mod x to the first power, say, okay? Then what happens? What is the equilibrium measure there? And this is the sort of fascinating part. We have not been able to prove this as yet. It's just very recent sort of discovery. This is a histogram again, where the equilibrium measure, the continuous equilibrium measure, is approximated by the discrete minimal energy problem. And what we see in this histogram, what is plotted, is the norm of these points, okay? And you see that they are sitting essentially between two values of R. One is sort of 0.48 or something like that, and the other is like 0.58. The other coordinate is number. Okay, this is 10 to the 5th points, and this is a density, I think. Okay, and what you see is that all of your points are between these two spheres. Okay, they're all between two spheres, and that's showing these are sort of the radial parts. So we're looking at the rate. Okay, these different spheres inside, and you can see that it looks like it's some kind of washer or something between, or annulus, right? Instead of mass between two.
So you can polar coordinate. Like
Yeah.
Theta,
Yeah, that's right. Yeah. So these are just the cross section. And so okay, so these are so this is totally unexpected. So why, if you have a log gas and you're looking at this external field, you should get the equilibrium measure, which is supported on an annular type of region, a 3-dimensional annular region. So we don't have an answer to that. Okay. If you look at other situations where S is subharmonic, okay, and here's a case where we're looking at a Riesz parameter S, which is D minus 6. And we're taking dimension 5. So if we're looking at dimension 5, again, we're looking at a histogram of these point configurations. And what we see here is that there is mass, definite mass accumulating on some kind of sphere, but then there's no mass. And then it looks like there might be a ball with possible mass on the boundary. So here you might have a sphere, and then as part of your support, and inside that sphere, a full dimensional object, a ball inside a sphere, a disconnected type of support. So okay, so I think
There must be some polynomial, maybe. Or,
a polynomial.
when it's zero,
Yeah.
zero.
Yeah, I don't know how to get a handle on this yet. As I say, it's a kind of recent discovery, and this is sort of what I regard as a phenomenon. I have no idea why that particular external field should cause the support to be disconnected. Okay, sure, it's radial. Okay, but why should it be disconnected? And how to get our hands on obtaining a formula for these radii. I gave you one simple method here, but that worked for a ball if we, have simple objects. It's not so simple even to find an equilibrium measure if I give you an annular region. Okay, reach to the ball. What's the answer for the equilibrium measure on an annular region? That's not known. That's not explicit. Okay. Okay, so let me just blow your mind with one last picture. So this is the end of the talk. And this is so namely, we suppose we go beyond radial. This is not a radial example. So we are looking here at 10 to the 4th points. We're looking in dimension 4, but now our external field is given by a power of the norm, but the norm is the LP norm where P is 4, okay? Where P is 4 in this 4-dimensional space. So if you apply the Laplacian, you see that whatever answer you come up with, it's got to be uniform. It's a uniform distribution, okay? Now, we have problems picturing things in 4 dimensions, right? So we took what we found for the particle case, for the discretized energy problem, and we look at it here in 3D, okay? We're looking at it in 3D. And so what we're seeing, we're trying to understand. First of all, there seems to be a spherical hole in this thing, okay? Which is kind of reflecting the kernel. And then the external field V is like the ball, the LP ball, right? Where P is 4. It's sort of looking at, so it's not circular, right? But this is kind of what we're seeing in these pictures is sort of reflecting this kind of behavior of this function. So we're seeing this object with that has both circular symmetry and the symmetry given by the external field. Right now, we have no handle on how to describe that. We don't even know whether it's full dimension or not. Okay, yeah.
Did you try to project on another, not a coordinate direction?
Oh, yeah, we did. Well, on the standard coordinates, there's no point. You just see the same thing.
No, but I mean, this is like if I look at the cube and I look just straight on and it looks like a square. So you get a 4D cube, right?
Yeah.
That would be a 4D cube, and here by chance you look at the direction where it looks like a 3D cube.
Yeah. So, well, I don't think there's anything gained by looking at, I mean, I can.
So it's really a 4D cube.
Yeah, it's a 4D cube, right? So every picture, every projection is going to look the same, essentially, right? You can look at the bottom, that kind of thing, but it doesn't really give us any greater insight. Yeah, so this is a kind of fascinating thing, how to handle other types of non-radial type of symmetries, and to what extent it inherits the symmetries of your external field.
Why did you do it with B equals 4? Because
Because I wanted uniform.
You can only subtract the even numbers from B. So you couldn't do B minus 3 in 3 dimensions. But, yeah.
No, yeah, but we also want to have a uniform distribution. So when we take, I mean, Frostman's properties hold and all that sort of thing, right? But if you apply the Laplacian here to this V, you're going to get a constant.
I mean, that's what, my question was why 4 and not 3? Why did you?
Because we're taking the Laplacian in 4 dimensions.
Because you want.
And I wanted uniform. I want, this is a uniform distribution in some sense. In the sense that the Laplacian is
You
constant.
wanted to have us power of the Laplace.
Yeah. Yeah. Okay, so anyway, just to sum up, is that I've talked about classical problems in potential theory. And what we find is that there's still some surprises. There's still work that could be done, interesting work and challenges dealing with the classical problems in potential theory. So, okay, thank you. Thank you for listening. And then Alex will take over.
So, any questions? Other questions before Alex takes over? You have a question?
Yeah. So, so one thing, great examples and mostly your T minus 4 theorem. So I have a kind of general question. So when you try to derive an equation for the equilibrium measure, there are two possibilities. Either you can get away with a mean field model where you see a sort of kernel of sort of mu of x times kernel k of xy and then a mu of y and that thing integrated. So that would be sort of a mean field description of the equilibrium measure, but it could also be in some of these field cases that you need to go to next order and have an equilibrium equation which involves correlations. So
Yeah. We have not done that.
Insights into how this equilibrium equation would look like. Do you need the correlations, or can you get away with the mean field thing with it?
Yeah, I honestly don't know. We haven't looked at the mean correlations at all. So I really don't have an answer to your question. It's all pretty new stuff. But that might be an approach to look at next order terms, so to speak, and correlations in that sense. So we haven't done that. No. So there's a discrete problem and there's a continuous problem. So you're talking about the discrete problem, right? Yeah. So that in the corrections for that, right? So yeah, I mean, yeah, these higher order terms are challenged even on the sphere, right? I mean, so the next order terms or correlation terms here we haven't explored. Any other comments or questions? Okay, so I think Alex is on board to talk, so I'm going to leave here. I think I'll try to leave. Leaving. Yeah. Okay, I got to.
All right.
Get this out. This out.
Okay, so can you hear us, Alex? Sorry, there is some the sound that you are
Oh.
Okay, can you search right now?
This.
Try to speak so we can check which is the microphone that is connected to the ears. No, not yes, sorry. No. We are trying any feature.
Do you mind? Does it work?
It works now. Suddenly it works.
Can you hear me? Okay, it seems to work.
Yeah, everything works. Okay.
Okay.
So really, we have 20 minutes more. Okay, so how much time would it be feasible for you to?
Oh, okay. So I can stop very. So we can go as short as you guys like.
Okay.
So you want to stop me when at 10 minutes to the hour? Is that right? Or
I mean, it could be 10 minutes to the hour. That was the original plan, but if that's too little, then.
okay. Yeah, I can try to do that. Mircea, can you just enable the screen sharing before you go away from the? Because right now it says host disabled participant screen sharing. So right now I cannot.
I'm on it. Okay. Make co-host. So now you're co-host.
I'm co-host, so I can probably screen share. Right. Okay. So so I have another hour. So this is not the last 20 minutes that I have for exercises, is it?
Unfortunately, this kind of.
Okay.
I mean, the coffee break is supposed to end at 11, at 11.
No, right. So what's the plan for the afternoon? Do I have another hour? Sorry, it's in the schedule, but we have diverged from schedule. So there is another slot in the afternoon, late in the afternoon, right?
Yeah, right.
Okay, great. So then, right. So then, let me just tell you what the plan is. So the plan for the afternoon, and accordingly not the plan for now, right? So the plan, so that you guys know what you will perhaps come back to, right? So so it is exactly what Ed mentioned earlier, right? So that's basically classical, this classical potential theory, and remove the quasi-everywhere from Frostman, and then maybe talk about the second order condition. So something like there was a question from the audience 2 minutes ago, right? And the question was something about the second order conditions. And maybe if we have time, that's what we'll talk about. So basically second order conditions for minimizing measure. Okay, so that's kind of the plan. So right now, since we have very little time, I'll just make some parting remarks. Some parting remarks on our Gegenbauers, right? So we talked about this optimization business and so on, and so you guys are now experts in optimization. obviously. I just wanted to make this comment that sometimes these Gegenbauer polynomials, so maybe this is a 15-minute worth of a comment, and it goes like this. These Gegenbauers, they come up as functions that preserve positivity, right? So come up as positivity preservers, let's put it this way, and I'll explain what I mean by that. So here is an example, preservers from or a statement maybe. Of the classical Schur's theorem, right? So okay, so this is a theorem due to Isai Schur. It's a Schur theorem. Very good name for a theorem. If you're prone to make puns, this is great. You can have a lot of fun with it. Say you have two matrices. Let's say square matrices of the same size. Such that they are both positive semi-definite. Right, so this is just saying that they are positive semi-definite. So maybe let's say they're symmetric, just to explain what this means. Okay, so this just means that the quadratic form, right? So you can write a quadratic form. So this is a vector, let's say matrix. Okay, this is an explanation what positive semi-definite means in case you have doubts, right? This means that this quadratic form is non-negative, and you would remove the semi. You would just say positive definite or strictly positive definite if the equality here implies x is also 0, right? So the quadratic form is non-negative. That just means positive semi-definiteness, right? Okay, so then, given these two matrices that have this property, then the Adamar product is also positive semi-definite, and I should really try to draw this. Okay, and this here is Adamar product, and what it does, it just multiplies entries of your two matrices, and places that into the entry of this guy. So this is Adamar product, and what it does is well, just this. So if you look at the ijth entry of this Adamar's product, it's the ijth entry of matrix A times ijth entry of matrix B. So that's that, right? As opposed to the usual matrix product, it just multiplies entries like that. Okay, so this is a well-known sort of classical fact in matrix analysis. So what I wanted to point out is a recent, maybe you can call it improvement, recent improvement or version of this theorem. And then I'll explain how to obtain this version really quickly using Gegenbauer polynomials. And that basically will be an illustration for what this this notion of positivity preserver was about. So version of this theorem due to Jan Vibirl. Okay, so this needs diacritic like that, and this is, I think, from 2020. Yeah, so it goes like this. So the interest of this version of Schur's theorem that Vibirl was why Vibirl was concerned with this. So he proved Novak's conjecture, which has to do with numerical integration. Okay, so just what this paper does, it proved something called Novak's conjecture in numerical integration. So anyway, has some more or less practical interest to us. It's just a statement about matrices. So what's the statement about matrices? So given a square matrix M, right? So it lives in matrices of size n squared. So this matrix is positive semi-definite. So you have this improvement. So if you Adamar multiply M with itself, Schur's theorem just tells you that this is positive semi-definite, right? So Vibirl came up with this improvement, which says not only it is itself positive semi-definite, but in fact, if you subtract another positive semi-definite matrix from it, it remains positive semi-definite. So, all right, I have to tell you what this right, so this is the let's see, the vector Coulomb, which contains exactly the diagonal of M. And this is, okay, do I have it wrong? Is this a row? Anyway, so this is either row or column. I can't think of the right orientation right now, but the point is the product is supposed to give you a square matrix, right? And this is the matrix product. Yeah, so this is a column and this is a row which contains exactly the diagonal of M. So if M is a covariance matrix, so it has a unit, it has ones on the diagonal. If it's a covariance matrix, then this is saying, right, so this is just saying the diagonal of M is all ones. It's all ones, and okay, I'm not sure how to write an all one vector. Yeah, so dots I think is a good compromise, right? And then this is a maybe this is a column vector, and so this is greater than or equal of a matrix of all ones, right? So not an identity, but a matrix of all ones. Okay, so this is clearly an improvement, and again, this you should understand also in the sense of this order of matrices, which corresponds to positive semi-definiteness, and this is just telling you that the difference is positive semi-definite. Okay, and so Vibirl gives proof of this, and he basically more or less repeats. Well, he says I haven't try to understand his argument, but he says some ideas are reused from Schur and so on, or at least in spirit, it's similar to Schur. But here's a very short proof of this inequality. So short proof, okay, of this fact using eigenpowers, which shows how you can often apply them, or what they are often useful for. So here goes. So let's take the covariance matrix, right? So the general case reduces to this case just by rescaling. Okay, rescale your coordinates appropriately, and you get this. So without loss of generality, M is a covariance matrix. Right, which means that there is a set of n vectors in Rn such that they lie on the unit sphere, and the dot products are exactly the entries of M. That's another way to state the same thing. Right, so hence there exists x1, so these are vectors in Rn, or I guess I should say in the sphere, such that the ijth entry is exactly the dot product of these guys. Okay, so this brings us to the sphere, right? So in order to apply eigenpowers, we have to go to the sphere, and so use this fact that the function. So here is a function of a single variable, which is t squared minus 1 over n. So I guess it depends on the n, but let's fix the dimension of everything that's going on. Let's fix it and look at this function. And so this is the second Gegenbauer polynomial in exactly the dimension that you need, right? So, okay, so you look at the sphere, you project a uniform spherical measure onto a diameter, you construct orthogonal polynomials with respect to that, and so on and so forth. Then you take the quadratic polynomial. Okay, here I'm deceiving you slightly, right? Because it's up to a positive constant, up to a positive factor. But that obviously doesn't change anything in terms of positive definiteness. So, okay, so I should tell you what to do with this f, right? So, and use that matrix M is, so this is a covariance matrix is positive semi-indefinite, implies that f applied to M is also positive semi-definite. Right. So, okay. So first of all, let me convince you that this is exactly what we are saying. What we are saying here. Right. So this part is clear. We just square every entry, subtract 1 over n. Okay. That part is fine. So if we can convince ourselves that this implication is right, then we're done. Right. So is everybody convinced in this fact? So modulo this implication, we are done, right, with the proof. If we can indeed say that this matrix, which has entries, right, so the ijth entry is exactly f of mij. Just apply entry-wise in the spirit of Adamar product. You apply your matrix entry-wise. That's that. So if we can justify this implication, that's exactly what we want. So these Gegenbauers or any positive definite function on the sphere is an entry-wise positivity preserver, right? So that's the point. Right? So exactly what it means. Yeah. Okay. So now, any ideas as to how we might check something like this? So let's call it a star or something. So to see star, apply the only useful fact that we know about Gegenbauers. So to see star, apply addition formula. So remember, Gegenbauers, all of them, where so let's say P2 of T, or let's write it this way: P2 of anything that looks like a dot product of two unit vectors is the sum of spherical harmonics of that degree, right? Also of degree 2. So you have some sum. So you have to go to the right dimension, whatever. There is a finite number of spherical harmonics. The important part is that basically Gegenbauers split like this. And so just like we had non-negativity for Gegenbauers themselves, we proved non-negativity of a matrix that you obtained by applying Gegenbauer to something that's positive semi-definite, right? So so what is now this f of m is positive semi-definite because let's take any vector, right? So let's take a vector, let's say C, which lives in Rn, right? Quadratic form, right? And then here we have this second Gegenbauer and so on of Fij. So first we use the fact that M is a covariance matrix. And then we use the fact that it's also a Gegenbauer, right? So this is F of Xi. I shouldn't. Right, so this is our quadratic form, Xi dot Xj, and then addition formula comes in, and we are basically done. Okay, so here maybe I need some kind of normalizing factor. So if you're super careful, or if you know this stuff, then you might notice that I'm actually, not being super careful, but all the factors that I may be dropping are non-negative. So no foul play involved. So this is in Ij, this is in L. Then you swap the order of summation, obviously, and you have a sum of squares. This would be Xi. This would be Xj. All right. So moral, this is non-negative because sum of squares. So verify this if you don't believe me. And so what's the conclusion? Well, Gegenbauers certainly preserve positivity, right? If you apply them entry-wise. Now, Okay, can I spell this? This is rather difficult. Okay. But not only they are positivity preservers, so that's easy. That comes from addition formula, but also this is precisely why they are valuable. It's because well, Schoenberg shows in 1940s anything that's a positivity preservers for arbitrary sized matrices is a series of Gegenbauers with non-negative coefficients, right? So any positivity preservers, any positivity preserver, in the sense that you have, what does it mean exactly? You have a matrix which is positive semi-definite, apply F entry-wise to it, you get something that's also positive semi-definite, is a series of Gegenbauers. With coefficients which are non-negative. Okay, and then, okay, this is where I really have to stop, but just to mention that this is somehow, this entire theory somehow has seen a revival, and there are some recent developments where people study their papers by Kare and co-authors. There is one by Kare Tao, where they look at positivity preservers for a fixed number of vectors, right? So, so right here we get a positivity preservation regardless of whether we take 10 vectors on the unit sphere or we take 20 or 200, doesn't matter, right? The Gegenbauers will preserve positivity in any situation. So there are some recent results where people classify positivity preservers in finite dimensions, meaning you take exactly 20 vectors and see what comes out of it. But that's somehow much more delicate theory than the classical stuff due to Schoenberg. So really, it's beneficial to read Schoenberg first before going elsewhere. Okay, so I'll stop here. So hopefully I've convinced you that Gegenbauers are not just some orthogonal polynomials which abstractly live in, in the theory of orthogonal polynomials that do not show up elsewhere. So thanks.
Yeah, okay,
So,
thank you. Are there any questions? Seems that nobody, but anyway, we will have time also later. Please prepare questions for later for Alexander and
Sure.
okay, so I'm going to stop the record.
All right, so you guys enjoy your lunch.